when I say in the future diagonal matrix, we know what we mean by this. Another shape of a matrix which we like in numerical application because it's easy to solve linear equation system is what's called triangular matrices. And that's really now what we mean, where the row echelon form, for example, comes in. The row echelon form is something what is an example of a triangular matrix. So that's the next definition we have. So again, we only talk about square matrices. So a square matrix A n times n is called upper triangular. If Aij is equal to 0, if, oh God, sorry. If I is larger than j, so that means if Aij is 0 below the diagonal, and it's called lower triangular, if Aij is equal to 0, if j is larger than I. So that means all entries to the right of the diagonal is 0. So just as an example, so upper triangular, let's put it here, upper triangular, here lower triangular, so an upper triangular matrix looks like this. So you have numbers along the diagonal. Then you have numbers here. And these can be any numbers. You don't really know. They can be zeros. We don't know. There's no condition on these. But the important part is, maybe I make it in red, upper triangular means everything below the diagonal is 0. So essentially, when you ask where is the triangle where the non-zero number is diagonal and to the right. So this is your triangle where you can have arbitrary numbers, but below the diagonal has to be 0. And similar now for the lower triangular matrix. I think you had similar homework question. I also assigned something like this. So you have, again, we start with a diagonal. And then, for example, here's A21 up to AN1. So here are numbers which we don't know what they are. They can be anything. So this is your triangle. But to the right of the diagonal, everything has to be 0. So lower triangular means only on the diagonal, and lower can be arbitrary numbers. To the right, everything has to be 0. Upper triangular means only on the diagonal, on top can be arbitrary numbers. Everything below the diagonal has to be 0. And again, what is the idea here? Where did we see things like this in this class? It turns out until now, we only saw upper triangular matrices, and the prototype for what we saw in class of upper triangular matrices are the row echelon forms. When we do the Gauss algorithm without the Jordan part, we generate an upper triangular matrix. So that's the goal of the Gauss algorithm. And we know if all these numbers are non-zero, we can make leading ones, and then we can find the inverse. That's actually what the Gauss and the Gauss-Jordan algorithm told us. No? So if these numbers are all non-zero, then we can make zeros on top, and we can find an inverse, or you can solve a linear equation system in a unique way. And all these results now are in the next theorem, which has some properties of upper and lower triangular matrices, especially the one I just mentioned. So in, let's say, if you do Gauss algorithm, we know we reach this staircase shape. We call it staircase. Now we can also call it upper triangular. And if these numbers are non-zero, we always divide each row by this number to make it a leading one. Then we eliminate on top and we can find an inverse matrix. No? Okay, so, and the result is called 1.71 in your book. And so these are some nice properties of upper and lower triangular matrices. Also, you see, if you take an upper triangular matrix and you make the transpose, remember transpose means you switch rows and columns, then if you transpose an upper triangular, you get a lower triangular, and if you transpose a lower triangular, you get an upper triangular. So they go back and forth with the transposition operation. So this is the next result we have. So in your book, that is theorem 1.71. I actually only like to go over one of these. The rest, it's not that it's easy, but there is a lot of calculation, and some of them I think are also clear from the Gauss algorithm. So here we have A and B, n times n square matrices. Then we have the following. Although the first one is clear, so there's nothing to do. A lower triangular implies A transposed is upper triangular. Same thing if A is upper triangular, then A transposed is lower triangular. Part B is now about multiplication. Again, we have nice properties here. When A and B, if they're both lower triangular, then A times B is also lower triangular. So the property is preserved under multiplication. And the same thing again, AB upper triangular implies A times B also upper triangular. So that means this is a property which stays stable under multiplication. So you don't lose the property. If you multiply two upper triangular matrices, you get an upper triangular matrix. Part C now is, that's actually what I just explained from the Gauss algorithm. So we have A upper triangular or lower triangular. Always think just about the upper triangular case, because you can go from lower to upper by just transposing, and transposing doesn't change properties like invertible. Then we have the following result. A is invertible if and only if all the diagonal elements are non-zero. And another way, math people are usually lazy, so we like to write this in a formula. How can we say that all diagonal elements are non-zero? It means if you multiply them all, you don't get zero. So another way of writing this is I goes from 1 to n. This is the product sign. AII is not zero. That means none of these elements can be zero. If one of them is zero, it's over, because then you cannot make a leading one anymore. Okay, so this is one. And then finally, the last one. Now we know that for triangular matrices, it's very easy to see if they're actually invertible. You just look along the diagonal. If there's no 0, then you know it's invertible. Doesn't mean you know the inverse, but it's also not too complicated to calculate it. It's just the Jordan algorithm to find the inverse. And but once you calculate the inverse, it's also nice because the inverse of an upper triangular is upper triangular and the inverse of a lower triangular is lower triangular. And again, you only need to understand it for upper because the rest is about transposition. So again, we have something like A.
Professor?
Yes.
What next to the A, is that an I or is that
yeah.
an I?
Yeah.
Okay.
Yeah,
Okay.
it's I. It means the diagonal.
Okay, yeah. I was just
so like something like A11, A22, A33, no?
Yes, thank
And
you.
you multiply them all. And if the product is non-zero, you know each of the numbers is non-zero, no?
Yes.
It's just a complicated way of writing this, no? All diagonal ments are non-zero. I mean, this is shorter, but that's easier to understand. But it's actually the same once you start thinking about it, no?
Yes, thank you.
Yeah, always ask. Yeah, it's always a chance that something is wrong here, but all right. So it's always good. So if A is upper triangular, and invertible, again, that's easy to check. Then it follows that the inverse, not that only does it exist, it's also upper triangular. And again, it's actually not difficult to see. Just think about if you would do the Jordan algorithm for a matrix, which is already an upper triangular shape, you only get entries above the diagonal on the right-hand side if you run your algorithm to find the inverse. Also that's actually not difficult to see. So this is upper triangular also. And the same thing with lower triangular, because if it's lower, you just repeat the same argument for the transposed and then transpose back. So a lower triangular and invertible means A inverse is also lower triangular. And as I said, this comes right away off the Gauss algorithm, then also this here. This is easy to see if you switch rows. And if you really like to show it, like in those of you who go to mathematics, I don't know, 350 or 270, who know how to do proofs, if you really do a proof, it becomes kind of involved with all the indices. So that's the reason why actually, the main reason why I don't like to do it, because then I end up in an index battle here. But otherwise, it's not difficult to see actually why this is. So I like to just show you one of them. So you see a little bit what the argument is here. So, and I only show, I think, I was thinking about this one, part B, this one. So only for plus. So you see a little bit how the argument goes. So here we assume A and B upper triangular, no? So A, B, upper triangular. Keep in mind they're always n by n. So that means Aij is equal to Bij is equal to 0 if you're below the diagonal. Means the row index is larger than the column index. That means below the diagonal. Then you define the product and have to give it a name. So I just call it C, very uninnovative. I just multiply AB and the result I call C. Then we have to show that for the matrix C, the same property holds, and we are done. So to show is Cij is equal to 0 if I is larger than j. So now to show this, let I larger than j. Then what do we know about Cij? This entry Cij of our matrix C. Also this should be actually a small c, sorry. My small c got big. Okay. And according to the matrix multiplication, we can write down a formula right away. So we can say, oh, this is just k goes from 1 to n, multiply row I of A with column j of B. A I k times B k j. There's nothing wrong here. Okay, it turns out this formula is not really clear. I mean, if you're a little bit more used to working with sums, then you can also use this formula. But I just like to really rewrite the formula and look a little bit, what are we actually multiplying here? So this time I go actually backwards. Usually I say this is better because it's shorter and better to see what it really does. But this time I do it the other way around. So that's AI1 times B1j plus AI2 times B2j plus dot, dot, dot. And then I'm kind of, the important point is the switch comes along the diagonal. So I stop essentially in my formula. I say dot, 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 but then I say at the diagonal, I look more closely. Looking more closely means I write a few more terms. So here's now AI, I minus 1, BI minus 1j, plus AII, BIJ, plus dot, 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 and then the last one would be AIN, BNJ. Okay, so this is just written out what this means with two dots here. No? And now we see BI1, BI2, BII, sorry, not BA, AI1, AI2, AI minus 1. When you look at all these pairs, I1, I2, I minus 1, each time the first index is larger than the second index, which means it's actually 0. So we know this is 0, we know this is 0, we know this is 0. We don't know what the b's are, but we don't care because they're multiplied by 0. Okay, so up to here, everything is 0 because all the a's are 0. But now AII, that's a diagonal element of a upper triangular matrix. AII can be non-zero. That's possible. But we are lucky because BIJ, I is larger than j, so we know this is 0 now. Now what would be the next term? Would be BI plus 1j. But if I is larger than j, then I plus 1 is for sure larger than j. So it turns out starting from here, all the b values are guaranteed 0. So that means if every term here is whatever the a's are, we don't know, but they're multiplied by 0, so we know also this is 0. So it turns out this whole thing is 0. So we have shown if I is larger than j, Cij is 0, therefore C upper triangular. Yeah. So this is the kind of argument which you have to do here. The same as a lower triangular would be absolutely the same when I write it like this. I'm just starting first with the column and then looking for the, first with the B matrix and then with the A matrix, because here when we're coming from the top, first the B elements are all 0 and then the A elements will be 0. And the same thing with invertible. It's very similar arguments in the sense that we have to look at a lot of these indices and see if they're 0 or non-zero. What can you do in the Gauss algorithm? Okay, so for this reason, I leave it like this and just show you one thing. But I hope all of these make sense. And I think some of these things, like part C, you have to apply in your homework also. So they ask you, for example, a triangular matrix, upper or lower. Can you tell me right away if this matrix has an inverse or not? And it turns out with this formula, it's very easy to show, oh yeah, because all the diagonal elements are non-zero, so the matrix has an inverse. Or if there's a 0, then it's not invertible. Okay, so I think this finishes now about our triangular matrices, where we have two types, above and below the main diagonal. We never look for the other diagonal. We always look the main diagonal, A11, A22, ANN. So that's always what I mean by diagonal. And so the last one, when you look at the title of this section, was about symmetric matrices. So that's something, the last definition. And again, many of the things are kind of obvious, and then 2 or 3 little things we actually will show in class. So let's do this. And then after we do this, we have our break for today.